This is Xtalpi Shorts Episode 2, where we will overview the MicroED workflow and introduce two case studies that demonstrate useful applications of MicroED to solid-state R&D. The MicroED project workflow starts by dispersing a crystalline powder sample onto a transmission electron microscope grid and then freezing the sample with liquid nitrogen. The sample is loaded into the TM and the imaging mode is used to identify microcrystals on the grid. Once suitable crystal particles are identified, diffraction data is collected on each of the microcrystals. The diffraction datasets are pooled to obtain a three-dimensional diffraction pattern. Using the 2D diagram of the molecule and the electron density, a solved crystal structure is proposed. Now that we know the basics of a MicroED experiment, let's look at two case studies. Determining a salt from a co-crystal can be a challenge. To do this, we need to resolve the position of hydrogen atoms. In MicroED experiments, if the hydrogens have a strong contribution to the diffractions, we can resolve the hydrogen positions and we can determine if hydrogen transfer occurs between the active ingredient and the ligand. Furthermore, if the sample is a salt, we can determine which atom in the active ingredient is protonated or deprotonated. Take yohimbine hydrochloride as an example. The first figure shows the initial structure without hydrogens added. It's ambiguous if the structure is a salt or a co-crystal. The small colored dots in the second image are the peaks in the electron density distribution map. The red arrow indicates a peak near the nitrogen atom. After structural refinement, all the hydrogens can be resolved in the structure. In the third figure, the arrow indicates the electron density distributed around the hydrogen. The structure is clearly a salt, and the indicated nitrogen atom in the yohimbine molecule is protonated. We must determine the absolute configuration of molecules in a crystal structure because chirality can determine properties like biological activity. For example, when the structure of glutamine is solved by MicroED, the non-centrosymmetric crystals formed by this chiral molecule could be one of two inverted mirror images. Absolute configuration can be determined directly by dynamical refinement. Dynamical refinement uses non-centrosymmetric scattering events to determine the absolute configuration of the molecule. Alternatively, if the configuration of a single chiral center is known, then the absolute configuration can be determined. A counterion or coformer of known chirality can be introduced to determine the absolute configuration directly. If you want to learn more about MicroED, then visit Xtalpi's website where you can watch the full webinar, MicroED and its applications in solid-state chemistry.